Hello. For our linear algebra presentation, Laman, Zineb, and I will be talking about the application of linear algebra to neural networks. So first, what is a neural network? A neural network is a subset of machine learning, and they are central to deep learning algorithms. They are modeled off neurons in the human brain, so each neuron contains input information that can trigger a response when the right combination of neurons are activated. And just as how in the brain, one neuron can activate another, in neural networks, activations in one layer of neurons determine activations in the next layer. So looking briefly at the structure of a neural net, there is an input layer on the left-hand side of this diagram and an output layer on the right-hand side. And in between are hidden layers, where most of the computation happens in the network. There's just one hidden layer in this diagram, but there can be any number of hidden layers. Usually more complex systems will have more. And there are connections between the neurons in adjacent layers, and each of them will have an associated weight.
So the math of a neural net, just using one, for example, the node B1 in our hidden layer here, it would multiply each input by the associated weight on the connection, and then add those values together, and then additionally add a bias, which would be specific to that node. And then that number gets put through an activation function, which essentially outputs either a 0 or a 1. So the most basic version of that is the step function, but more often it's something more complicated like sigmoid, which we have also pictured here. So the linear algebra part of this is that the process of multiplying by weights and then summing them can be written as the inner product of two vectors. And then furthermore, if we represent all the bias values as a bias vector, then we can use a matrix of weights and multiply it by a vector of the input values and then add the bias vector. And then we just get a linear algebra equation. And then we put all of that through the activation function. So this image explains a little more clearly what I'm talking about. There's a matrix of weights associated with each connection that gets multiplied by this input vector, and then you add the bias vector and put it through F, which could be anything. So for training the neural net, that's most often done through a process called backpropagation, which does not involve linear algebra, so I won't go into too much detail, but it does use multivariable calculus. So if you want to look it up, you might be able to understand what they're talking about. But essentially, you pick a function that can assign a numerical value to how badly the neural net does each time it produces a value based on the training data. And then it uses that number to correct the weights and biases in the network. And the reason why linear algebra is such a significant part of the neural net is that it turns out that computers are optimized to do linear algebra computations a little bit faster than doing each of the individual multiplications and additions. So when training on really large data sets or just really large data, this can save a lot of time.
Okay, so we can use neural networks to predict outcomes. In this example, we'll predict a test score given hours of sleep, hours studied, and the previous test score. Randomly assigned weights will correspond to each of the inputs, and then a bias will be accounted for. Here, the bias is -10. The next node values will be calculated using this g of z function, where we multiply each of the weights by the input node's values, sum them, and then apply the sigmoid function to that sum. Here we have our parameters. We'll have some connections to the inner layers with associated weights. And again, these weights are randomly assigned by the user. Using those weights, inputs, and the bias, this is how we'll calculate the next node's values in a linear algebra related format. Here are resulting values. 3 of our 4 values are 1s, but for the purposes of the example and to demonstrate the significance of backpropagation, we'll continue. Now we assign weights to the connections of the output node, repeat the calculation, and achieve a final score of 14%. This isn't really a good representation of what the real score is likely to be, but this is why backpropagation is essential to the machine learning. To fix the score, we would likely have existing data from other students so that the machine could predict the test score more accurately. And then it would backpropagate to fix the weights and give a more reasonable test score that isn't failing. If our weights are correct, we would be able to use the neural network to determine how best to spend time preparing for the exam. Should you keep studying or should you get some sleep? On a small scale, neural networks can help determine the answer to these questions. Here's our works cited. We hope you enjoyed and thank you for watching.